So now that we have established that, I can define heat capacity. Heat capacity is the byproduct of the heat fluid theory. Do you remember the heat fluid theory?
They thought that heat itself was a fluid that transferred from one object to another.
Yes. So they thought that all objects contain this fluid called heat that transferred from one to another. Okay? So this is the byproduct of that theory. Not byproduct, it's a residual
Result.
No, it's like left over from that. This word is left over from that theory. How would I say that?
Residuals. Yeah.
Residual is good, right?
Result. Also.
It's not quite a result. It's just left over. So it's a wrong terminology, just left over from that idea. It is a relic and it should be changed, but you know. This is residual from the heat fluid theory. So we know that objects don't contain heat. They transfer energy when brought into thermal contact with each other, which then raises the temperature of one and lowers the temperature of the other. So then what is heat capacity? It is the amount of heat needed to cause, okay, tell me later, change delta T. Defined as C Q over delta T. So in words, it is the ratio between heat Q transferred to an object that raises its temperature by delta T. Note, I have not yet defined what delta T is. And in terms of the first law, I can also rewrite this as C could be defined as delta U minus W divided by delta T. So the definition that you probably are familiar with is this one. The amount of heat needed to raise the temperature of an object by 1 degree. 1 degree. What is wrong with this definition? So I should get a snail.
Yeah.
And a 0. And you would be right. And the thing you need to understand about this is that, yes, I do get a snail. There are no units. And number 2, I have not told you, even if I did tell you the degree, I'm not telling you whether it's Celsius or Kelvin or what kind of a degree it is. Number 2, I am also not telling you the amount of material you should have in order to raise its temperature. So if I had this much water, how much heat would that need to raise it by 1 degree? If I had this much water, how much would it be? If I had a pond, right? So there are many, many problems with this definition. Not only have I not told you what degree I'm talking about, I have also not told you what quantity of matter am I trying to heat. Will it be easier to heat this than this? If I had 10 of these and I had 1 of this, which could be heated faster? Right? I don't know. Well, yeah, probably this would be harder to heat, right? And this is just metal. It will be easier to heat. So all of this creates a problem. So instead, what we do is we define another thing that's called the specific heat capacity. Okay, and how do we define that in order to take care of it? If I have so many problems, how do I fix them? I need to get rid of the mass that's involved. Mathematically, what would I do? Divide by a mass. That will get rid of the mass in my equation. I have a mass in my equation. I just divide it by the mass. And what side do you think I should divide that with? C over M. That will get rid of the mass in my equation. So now it's, regardless whether I have 1 or 10 of those keychains, my specific heat should remain constant. And what I don't like is the fact that they defined this to be small c. And I can never tell the difference in my handwriting whether it's a small c or a big C. Well, this is my solution. I'm going to, what's the word? Cursive writing the C. And how will that equation change?
Dr. Zaid, it's all cursive.
No, my C, the little c is cursive.
But
Drum roll. Wait. Drum roll, guys. That's the expression you have seen. This is where it comes from. There's nothing fancy about it. It's all because of heat fluid theory. And what you may also have seen is something like this. So how does this become that? What's happening to the delta T? Right, it's very simple. Everybody with me so far?